As the nitrogen cycle progresses, amino acids are turned into ammonium and ammonium into nitrate. Now, if you go into the book, they'll tell you a little bit about the differences between autotrophic and heterotrophic nitrifiers. But it's important to know that there's a class of microbes that are nitrifiers that are primarily responsible for taking ammonium and turning it into nitrate. Now, part of the reason that this can happen is ammonium can be used as an energy source. If you remember, -3 versus +5. So there's a lot of energy in ammonium. And the autotrophic nitrifiers do this process of nitrification in order to gain energy from the ammonium. Heterotrophic nitrifiers produce nitrate, but it's not necessarily for the purposes of gaining energy. Now, when we've simplified the nitrogen cycle, we say we start with amino acids or dissolved organic nitrogen. It's mineralized to ammonium and then nitrified to nitrate. But this step right here, although it's done by nitrifiers, is actually a little bit more complex. So we can start with ammonium, but actually there's an intermediate step, nitrate, that's produced by one class of microbes, and then nitrate from nitrate. This tends to be a relatively short-lived intermediate. It's not present in high concentrations, and almost immediately is taken up and nitrified or oxidized further. You can see if we take a look at, we go -3, that's an intermediate redox state also. So in this case, ammonium is actually one of the intermediate steps is the production of nitrite and then nitrate. And nitrate can be present in some systems in relatively large quantities, but it's relatively rare. And in general, the microbes that produce nitrite and nitrate are present in similar amounts across different ecosystems. So nitrite rarely accumulates in the soils. When we talk about losses, this will become more important, but this is figure 9.9 shows different pathways of autotrophic nitrification and denitrification, as well as nitrogen trace gases that are emitted through different pathways. So this is just a linear chain. We start with dissolved organic nitrogen. These are amino acids. We have a mineralization or ammonification that happens where amino acids are turned into ammonium, and then the process of nitrification where nitrite and nitrate are produced. What happens to nitrate? There's a couple of them. And we'll talk a little bit more about this during the losses, but there's a whole series of loss pathways associated with denitrification that happen under a certain set of conditions. Nitrification itself requires oxygen because it's an oxidation of ammonium. As this proceeds though, as you go from ammonium to nitrate, what the authors want you to know is that you can also have gaseous loss that occurs during the process of nitrification. During these stages, there's a certain proportion of the nitrogen that goes through nitrification that's lost as NO or N2O. So in this case, nitrification, as it proceeds, there's a little bit of loss that happens from that ecosystem. So on this figure, dissolved organic nitrogen, ammonium nitrification, which happens under high oxygen conditions, but also you have an intermediate step with nitrate, and during the process of nitrification, you'll have some gaseous nitrogen loss. Just like we did for mineralization or ammonification, we can ask what are the short-term and long-term controls over nitrification. So what systems are going to have a lot of nitrogen being made available in inorganic form, and how, as well as that form being nitrate. So a lot of ammonium being turned into nitrate. Well, we know that ammonium is a substrate that's used to produce nitrate. So having a high ammonium concentration is a strong short-term control. In addition, it's an oxic process. So you need high oxygen concentrations in order to oxidize ammonium. So the two direct controls are lots of ammonium and lots of oxygen in order to generate high nitrification. The indirect controls, 1, 2, 3, 4, 5, 6, there's a lot of them. High ammonium concentrations happen when plants don't absorb a lot of ammonium, when there's a lot of litter around, so a lot of organic, particulate organic nitrogen, and carbon quality is also relatively high. In addition, you need to have high oxygen concentration, and that happens when roots and microbes aren't respiring a lot, when the temperature in water is relatively low. So if you have saturated soils, for example, you're going to have low oxygen concentrations, and different soil textures give you different oxygen concentrations due to the movement of oxygen through the soils. So a very fine textured soil, lots of clays, oxygen concentrations can be low. Sandy soils, oxygen concentrations can be high. So when would we have the highest nitrification rate? Well, not a lot of plants around, but a lot of litter, high quality of carbon, not a lot of respiration to use up oxygen, moist soils, but not necessarily too wet, and then sandy soils. So if you think about if there's a disturbance that happens to an ecosystem that shuts off plant ammonium absorption and allows ammonium to accumulate, and it's in a system where there's a large quantity of high quality litter, you're going to get a high ammonium concentration. And if you're in a relatively sandy soil that is not too hot, not too wet, but there's not a lot of respiration that's going on, that's going to give you a lot of oxygen. And that's the key systems where you'll get very high nitrification. In contrast, if you have a really wet soil on clayey, for a clayey texture, there's a lot of plant absorption that's going on, but not a lot of litter being produced. Nitrification might be pretty low because your ammonium concentrations are low and you might not have a lot of oxygen around. When we look across systems, the rate of nitrification varies from 0 to 100%. So there are some systems that have very little nitrification. You'll have mineralization and the production of ammonium, but very little of that actually is nitrified. So think about a low oxygen system. When the soils become anoxic, you just don't have oxygen around to oxidize ammonium. That would be on the 0 side of things. Sandy disturbed systems, for example, lots of ammonium around, lots of oxygen, nitrification rates very high. This figure 9.11 shows a relationship between net nitrogen mineralization and nitrification. And if you look at the scale here, 0 to 0, 10 to 10, 60, 60, this line right here represents 100% mineralization, 100% nitrification. So 100% of the nitrogen that's mineralized is nitrified. These are for tropical forests, for example, and it can show that across a wide range of ecosystems with a wide range of mineralization rates, the conditions can be right to give you almost 100% nitrification, which means that plants more than likely are going to see a lot more nitrate than they are ammonium. In other systems, nitrification rates can be a lot lower, and this isn't necessarily the case, that you would have 100% nitrification across all ecosystems. Just like we talked about the 4 fates of ammonium, there's also 4 fates of nitrate in soil solution. The first is that it can be absorbed, and we talked about immobilization, where nitrate in soil solution can be absorbed by microbes, and that's immobilization. It also can be absorbed by plants. So in this case, nitrate can be absorbed by living bodies, and that's one fate of nitrate. It also can be adsorbed, but you have to have anion exchange sites. So you have to have clays that have positive charges to them. And this can definitely happen, but as we talked about, it's relatively rare to have net anion exchange capacity within soils. Third, it can be lost via leaching. Nitrate is relatively mobile in soils because most soils will have a negative charge to them. So if nitrate's in a soil, it's readily lost from that system. And leaching is a big pathway by which nitrate in many systems is lost. When it's lost via leaching, that's where it enters the water. And ammonium, because of its positive charge, is a lot less mobile in soils. And so we see a lot less ammonium being leached into waters compared to nitrate. So leaching losses are a lot more prominent for nitrate than they are ammonium. Lastly, they can be lost via denitrification. We'll talk about this in the next section, but there's a series of pathways by which microbes can use nitrate as a terminal electron acceptor, and some form of nitrogen gas is emitted from the system. Now you'll also notice that one thing that we didn't say is that you're going to form minerals with nitrate. For the most part, all of the minerals associated with nitrate are soluble in water. So calcium nitrate, for example, or potassium nitrate are highly soluble, and nitrate doesn't form insoluble precipitates. So nitrate, once it's formed, doesn't get removed from the soil system due to adsorption very often, nor does it form insoluble precipitates. Lastly, the authors want to go through a little bit on temporal and spatial variability, and you can read about that in the book. There's variability in nitrification within soils, and it shouldn't be thought of as being uniform. For example, aggregates that happen in the soil have differences in the amount of oxygen and nitrogen availability. And some of the patterns of nitrification, for example, are going to vary on a very, very small spatial scale based on small microsites that differ in how much oxygen and nitrogen are available. There's also in many ecosystems temporal asynchrony to nitrification. Nitrification is a microbial process, and so for example, if you think about temperatures, it's going to go up with increasing temperature. But at the same time, it's also dependent on ammonium concentrations and plant uptake. So the more ammonium you have, the more nitrification you have too. And there can be asynchronies in the patterns of ammonium formation and uptake by plants, which can lead to times that ammonium concentrations are relatively high. So in some systems, for example in temperate systems, underneath the snowpack, early snowpack in the fall, you can have relatively warm soils. You can have ammonium being produced via ammonification, but this is not a time when plants take up a lot of nitrogen. So therefore, it's a situation where you can have high ammonium concentrations that are going to lead to a lot of nitrification. And all of that is going to happen underneath the snow in the ground. So it's not a time when plants are active, microbes are still active and producing nitrate. That being said, there are plants that actually have special snow roots that are active during this time and can take up ammonium or nitrogen. That's a small story, but still there's large asynchronies to plant activity and microbial activity that can lead to high nitrification at certain periods of time.